Morning, everybody. Thanks for joining us for another edition of our Science Talks webcast, where research meets production technology in the context of new things that are going to be visible and you can experience them at AMO Hannover. Today's topic is about three-dimensional electronics. So think about all the fancy items that you can buy that have really fancy shapes that are 3D printed. So the question is, how is this going to affect electronics? In 10 years from now, will hearing aids, smartwatches, and other products be directly printed, including their electronics? I think there's a lot of interesting questions in this idea. So I'm really happy that we can present to you today a presentation by the Institute for Factory Automation and Production Systems of Friedrich Alexander University Erlangen in Germany. And the speaker today will be Markus Ankenbrand, who is the director of the Mechatronically Integrated Device Lab. So Mr. Ankenbrand, great to have you here. And now let's hear from you what the future will be holding in terms of getting electronics directly into 3D printed or 3D shaped objects. The floor is yours. Go ahead.
Yeah, thank you very much for the introduction. I would like to start and directly jump into the obvious question, what are three-dimensional electronics? So we also call them mechatronic integrated devices. And the general idea behind those are that they are integrating different functions into a single part. So for example, as you can see in this picture, you have a 3D substrate and you have a three-dimensional layout, which is defining electronic functions. And by bringing those two together and adding electronic components, we can generate those three-dimensional integrated devices, which can not only combine mechanic and electronic functions, but also thermal, fluidic, or optic functionalities into one device. So I'm pretty sure that for those who are not directly connected with this kind of technology, it's hard to imagine what kind of products we can make of this. But I'm pretty sure you all know these AirPods from Apple, for example. And when we look what's inside them, we can see there's three-dimensional electronic that is acting as connectors between the different components, and also for the antenna functionality. And this kind of process I would like to tell you more about. And you can see, for example, the microphone or the headphones that are connected with this 3D MID. You have a substrate carrier which is holding the different components together, and onto the substrate carrier there's in gold circuitry and antenna functions. So this is the general idea, that you don't have a PCB board or a conventional circuit board, as you know, for example, from your computer, the green motherboards, which take much space. And the idea of the three-dimensional circuit carrier is that you can combine the mechanic functions of your part with the electronic or thermal or fluidic functions of your product. There are many other examples for existing applications. For example, infrared lighting modules for a camera, where the different LEDs are in an angle so that you can make a beam that is spreading into the room. This part here is a miniaturized control element for a dentist tool. So you have two buttons here, and the entire electronic is also on this three-dimensional circuit carrier that is perfectly adapted to the shape of the product that you want to design. And this is a motorcycle handle with buttons aligned in three-dimensional directions from BMW. And here you can also see the potential of this technology, that you don't need to manually solder these components onto the final product, but you can use this kind of circuit carrier with three-dimensionally aligned components onto it. So I would like to start with the most common technology that is used to creating these three-dimensional circuit carriers, or 3D MID. and the benefits of the different structures that you can generate with this technology. So you can not only make circuit traces on these structural parts, but also, as I said before, generate antennas onto the surface, use the existing mechanical part for mounting elements, for example, a battery holder that is directly integrated into the housing of the product. So you don't need a separate part where the battery is clamped. You just use the housing and the design process to directly embed the battery into your part. You can make shielding structures or security structures like this pattern for alarm systems. And if you drill into this housing, you will disrupt the connection of this meandering shape and trigger the alarm. You can also use it to fix components into a specific angle or to give an orientation of your parts. If you have, for example, a sensor that is detecting sunlight from different angles, you can use these chips mounted in a different angle. You can directly use also the injection molded part for contacting elements. So you don't need a specific contacting device. You can just use the plastic parts and metallize these pins, and then you have a connector. And you can even embed fluidic channels into your part for cooling functions or for sensors that detect mediums. And the general potential of this kind of technology is design freedom. You can embed different parts and thereby reduce the number of different components that need to be assembled. You can increase the functional density by using the housing directly as a substrate for your antenna, for example. You don't need to mount in a specific antenna part like conventional antennas, and you can reduce weight by this. It's obvious if you can use the housing directly to use as a substrate material, you can get rid of the conventional electronic circuit board. So the most common process for this is called laser direct structuring, and it consists of an injection molding process that is used to generate the mechanical part. Obviously, it requires a form, and the powder, the granulate here, is injection molded into the final mechanical shape, and then a laser is used to structure the layout onto this part. So it can be a three-dimensional layout. The laser can be directed and redirected with mirrors to reach any side of this component. And in a third process step, a chemical process is used in a copper bath. When the parts are dipped into this copper solution, then the copper will assemble everywhere where the laser has activated this part, and thereby leaving conductive traces on your three-dimensional circuit board. And then you can mount, for example, specific electronic components like you would on a flat circuit board, and they can be soldered with conventional methods, and then you get the functionality of a circuit board that would be much bigger into a three-dimensional shape. And also you can use the benefits that I mentioned before to force specific alignments of these components. So as you can already imagine, there are manifold advantages of this technology. However, there's also some drawbacks. For example, you always need a tool which are quite expensive. If you, for example, just need a prototype, then additive manufacturing is a very potential alternative for generating the mechanical structure. And also, if you think about personalized products like hearing aids that are personally fit to the patient, then you can use additive manufacturing to better adapt to different layouts or to better adapt to customer preferences or customer shapes of the desired function. So additive manufacturing has been used for many years, especially in the field of rapid prototyping, and there the focus was on geometrical objects. So there's no physical requirements, no big requirements consisting or concerning stress. It's just for example, this kind of design study or a prototype of a product that is later manufactured by CNC milling, for example, out of metal. So this was the first step where additive manufacturing was used. Nowadays, we are a step further where additive manufacturing can be used for mechanical requirements. For example, this structural bracket, additive manufacturing is even used in the aeronautic industry for making turbine blades out of metal. So this is the second step of the evolution of additive manufacturing, where you have also mechanical functions. And the next step that we see is the mechatronic systems. So you have not only have a mechanical body, but also add mechatronic functions or electronic features into these parts. So this would be possible for the before shown three-dimensional PCBs that you don't use injection molding, but additive manufacturing to generate this kind of substrate body. And then you can add electrical functions like circuitry, and you can replace cables by printing directly paste onto this additive part. You can generate antenna structures. You can have connectors or switches or shielding function directly integrated in your part, and sensor functions, for example, for touch sensors that are capacitive. You can have light sensors that are based on photovoltaic patterns, or even strain gauge sensors that can measure stress on your mechanical part. It is even possible to generate actuating functions like bimetallic actuators or electric motors and dielectric elastomer actuators. I will come to those later. These are basically artificial muscles that can be printed, and then you have a retraction or expandation if you add voltage to this. Then it's also possible to have control functions embedded, like optical waveguides that can conduct light, RFID antennas, or even OLEDs, which are organic light-emitting diodes that can be printed using digital printing processes. So for an example, for digital printing processes, I would like to shortly talk about the aerosol chip process that we are using in our lab. It is a contactless printing process that can generate structures smaller than 10 micrometers and up to 10 millimeters by a nozzle that is spraying silver or copper inks into onto your substrate part. And it is possible to use a wide spectrum of mechanical parts that can be printed on. And there are many different inks that can be used for generating conductive patterns, resistors or isolation layers, and even for building capacitors. So applications for this printed electronics are, as I said, capacitive sensors for measuring the height of a water level, for example, or for using antennas on your mobile phone housing. So the plastic part of the mobile phone can be used as a substrate part for an antenna, and this silver paste will be directly sprayed onto this part to generate these kind of sensors or antenna functions. And here's a short video how these kind of processes look like. So the first process is a inkjet-based process where you have a cartridge with conductive paste. So you all know the inkjet printers at home, the desktop inkjet printers that are using different colored inks, and in comparison or in contrast to this, we are using, instead of inks, conductive materials based on silver in this case, and the silver is then jetted with a piezo actuator onto your part. And then we have a 5-axis motion system that you can see here that is used to manipulate your part into different angles dynamically during the printing process. So it is possible to generate different layouts onto this substrate. It is even possible to generate this kind of pads that can be used later on for assembling light emitting diodes, for example, or different other electronic parts like resistors, and then they can be glued or soldered onto this part. So the second process that we see in this video is the aerosol chip-based process. You can see that the structures are very narrow. They have a width of 50 micrometers in this case, and you can also see the big standoff distance of several millimeters above the part, which is giving the benefit of high design freedom. So you can print into trenches or in between different shapes of your mechanical part without having a collision. And this wouldn't be possible with conventional roll-to-roll printing or desktop printers at home, because you need this kind of high standoff distance to reach different angles on your part. So we took this a step further, and we doing research in combining these two processes with machines from Neotech that are basically a 5-axis motion system with the capability of mounting modular tools. So we can mount different tools in a single housing, in a single process room, and thereby we can combine additive manufacturing, which you maybe know from the conventional FDM printers that are used to melt a filament out of plastic and to generate this kind of mechanical structure. And we can disrupt the process in the same process room and switch to another process, for example, the piezo jetting process, to contactlessly print silver structures into this housing. And we can even use a vacuum nozzle to place electric components into the part. And by combining these three processes, we can use different functions that are embedded inside a mechanical part. And at the end, we will close the housing and have all the electronics hidden inside the part. So we can really save space and use the additive manufacturing potential of customization and individualization for making specific products for different customers or with different shapes like they want to. And to demonstrate this, we have a time-lapse video that is showing the three different processes combined in the same process step. So we have the additive manufacturing module mounted here. At the front, we have the piezo jetting module that is jetting this electrically conductive paste. And then we have a vacuum pipette that can collect electric components from this tray on the right. There are some computer chips and resistors and LEDs, and they can be grabbed by this vacuum nozzle and placed directly into the liquid ink. And as you can see here, we are printing the mechanical part, and with the 5-axis system, we can also wrap around different conducting structures, and then we embedded components, and then we close the current layer with filament. So we print plastic directly onto the electronics to encapsulate them and to have different layers with different functionality hidden inside this part. So there's a computer chip inside, and the functionality of this demonstrator is an egg timer. So it has the shape of an egg, and there will be some LEDs outside this pattern, and it can be set to different times of minutes, and then it's counting down the different minutes and triggering an alarm when the time is up. So you have a functional demonstrator, and this is only to show you what kind of potential this kind of mixed technology has for products in the future. So you can think about not only this kind of toy feature, but also about hearing aids that can be 3-dimensionally printed directly with the components inside. And for example, the ear of the customer can be measured with the laser scanning process, and in the future, maybe directly in the hearing aid lab, you can print this kind of hearing aids or this kind of functionality while the customer is still waiting. And within an hour, he can take away his customized hearing aid that is specialized onto his ear. And for this part, we made an X-ray scan to show you what's hidden inside. So you can see the layers outside with the different LEDs. Here you can see the piezo buzzer that is generating a sound. And here inside, there's the computer chip that is connecting all the different layers with this kind of circuitry. We have different ramps that are connecting the different LEDs and the resistors all together to embed this kind of electronic functionality into a product, and the main components like the batteries are hidden inside, just showing you the potential of embedding different features for saving space, weight, and for individualization of products. So this was my overview of the technologies for three-dimensional electronics. I'm very happy for your attention, and I'm looking forward to your questions.
This is very valuable information with us. To the audience, if you have any questions, you have a questions or Fragen window in the dashboard of GoToWebinar. If you have any questions, just type them there, fire them off, and we can take care of them and discuss the answers together here. Meanwhile, what interests me is how ready is this process for industrial scale production? So are there any applications in industry as of today where 3D printed electronics is already in product?
Yes, so 3D printed electronics is basically can be used on injection molded parts, and there the technology is quite far, but I'm not aware of any products yet that are on the market using 3D printed electronics. There are many applications in 2D electronics, which is just roll-to-roll printing. For example, the RFID in these cards are printed. And for 3D electronics, there's still some research ongoing for improving the process stability, and the long-term stability of the printed parts also needs to be assured by using protective layers, for example, a varnish that is protecting the three-dimensional part from destruction by high humidity, for example. And in the additive field, I would say we're still this is just a proof of concept that we can use the combination of additive manufacturing with printed electronics, and there still needs to be a lot of research to be done how we can combine these different processes like additive manufacturing and printed electronics to make products available that are of high quality and that are working as well as conventional electronics.
All right, thank you. One more question. You mentioned that you were able to print copper-based and silver-based conductors. Are there any other materials that you can use, and what are the differences or the benefits of these materials?
Yes, so there's many different materials that can be used. There are many different metals. You can also use gold, for example, which is obviously more expensive. You can also use dielectric materials, like just a varnish for protecting it, or different resins that can be used to make capacitors. For example, you can use silver ink in one layer, then you can use a dielectric layer, and then you can use silver again, and then you get a capacitor. You can also use semiconductive materials. There are some materials that can be used to generate OLEDs or even to generate transistors by combining different stacks of material layer. And yeah, the second part of the question was of the differences of these materials. There's differences in the reaction on the substrate. So not all materials attach as well on specific substrates. You can print on many different plastic parts, for example, and in some cases the material needs to be adapted by adding acidic components to better have an adhesion between the ink and the component that you are printing on. There's also differences besides to the price of the materials, how you can connect electronic components. For example, the benefit of silver is that silver can be used in atmospheric environments, so you don't need to worry about oxidization of the silver paste, because silver oxide is also conductive. So it doesn't matter if you just have much oxygen in your process chamber, compared to copper, where it's very critical that you don't get copper oxide. because copper oxide is not conductive, and then you have the problem of very bad conductive properties. However, the advantage of copper is that you can directly solder onto this copper structure. You can use the conventional soldering process for mounting electronic components like you would on a circuit board. For silver paste, you cannot use soldering in most cases because the solder would resolve the printed structure and would destroy the printed circuitry due to chemical reasons, because there's also silver inside the solder paste. And that's why we use conductive glue when we are printing with silver. So there's also always different considerations that need to be made for deciding which material is best suited for specific applications.
All right. I don't see any more questions for the moment. So thanks a lot, Mr. Ankenbrand, for giving this insight into an upcoming technology, which I think is really interesting. And I think we need to pay close attention to how the developments will proceed from here. So to the audience, thanks a lot for listening in to our Let's Talk Science webcast together with WGP, the German Academy of the Production Sciences. And before you go off, just please remember that the next Let's Talk Science webcast will be on 30th of November. And there we will be discussing how sheet metal forming becomes more ecological and economical by getting rid of lubrification. Thanks a lot to everybody. Have a great day. Stay safe and sound, and see you next time. Bye-bye.
Thank you. Bye-bye.